Good afternoon. My name is Igor Ivanovich. I'm with the University of Michigan, and I'm really delighted to be able to speak with you today in this interactive fashion, in this innovative way on how we are doing the lectures this summer. I currently see 90 participants, so I'm really delighted to see a lot of names that I know and even more of them that I don't know about. So I would like to go ahead and share my screen now. So we'll and I hope I can, 1 second, just remove all the distractions here. I hope you can see this. Okay, today I would like to talk about the far-field reactor discovery and monitoring using antineutrinos. And this is a topic that is especially dear to my heart in the recent period. And this is a neutron week also. And I assure you that this also has a lot to do with detection of neutrons, as you will see. So by way of introduction, I would like to first give some recognition to Wolfgang Pauli, who is one of the pioneers of modern elementary particle physics. And Wolfgang Pauli faced this very difficult problem back in 1930s, where it appeared that there is a violation of the energy conservation in the process of the beta decay. And this was a significant problem that they tried to solve by introducing another particle into the process. And he called that particle a neutron. So this was in 1930, so 90 years ago. He postulated the existence of a particle that we call neutron. And in fact, later on in 1932, the particle that we call neutron today was discovered by Chadwick, and in 1933, this particle was renamed neutrino. He didn't take this really lightly. In fact, he expressed a very serious concern about this idea of a new particle. And he said something like this: I have done something terrible. I have postulated a particle that cannot be detected. And that is something a theorist should never do. And as we move on, to present time, things have changed dramatically. Neutrinos are being detected routinely, and so much so that even a whole new field has emerged that we call applied antineutrino physics, that concerns the various applications of antineutrino detection in other areas. And in particular, relevant to what I'm going to talk about today is the problem of nuclear proliferation. So this is roughly the overview of what I'd like to talk about today. First, I will just talk about antineutrino production in reactors, how many neutrinos are produced per unit time, talk a little bit about the safeguards of IAEA and how they address the problem of proliferation with reactors. Then I'll talk about how antineutrinos interact, how they're detected, and especially with emphasis on how they can be detected in large water detectors that are doped with gadolinium, which are one prime contender for detection of antineutrinos at large distances. I'll talk a little bit about a few use cases for detection of antineutrinos at large distances, and then finally highlight a few new technologies that may improve the process of antineutrino detection and capabilities and use cases that may be derived from those new technologies. So, when we talk about non-proliferation, one issue that always comes up is the fact that the civilian nuclear fuel cycle can be intertwined, with activities that result in proliferation. And there are several opportunities, for production and diversion of the special nuclear material that could be used for proliferation. And in regards to things that I like to talk about today, and where antineutrinos apply in particular, is this part here, which is the operation of a nuclear reactor, which is apparently only a very limited component of this nuclear fuel cycle, but also a very important one because this is where the plutonium is produced. And then there are additional applications, of detection of antineutrinos inside of the nuclear fuel cycle that have been proposed and considered, but they're admittedly significantly less developed, and they are still in a conceptual stage, and they concern detection of antineutrinos emitted from interim and permanent geological storage of spent nuclear fuel. So just to establish some of the typical scales here for plutonium production in reactors, we can consider two types of reactors. And the first one, which is very well known to the public, is a power reactor. And these reactors typically operate somewhere on the scale of 1 gigawatt electric, or maybe on the order of up to 3 gigawatt thermal. And for the purpose of estimating the proliferation potential, of these reactors, we like to quantify the production of plutonium in the units of what we call a significant quantity, which the International Atomic Energy Agency has defined as 8 kilograms for plutonium. Which is then associated with, with a significant proliferation potential or ability to construct maybe a single nuclear weapon. And 1 gigawatt electric reactor produces somewhere on the order of over 200 kilograms or 25 to 30 significant quantities of plutonium per year. So if one then considers production of maybe one significant quantity of plutonium per year as sort of an arbitrary but useful threshold for assessing the proliferation potential of reactors, then one can conceive that much smaller reactors could also present such a proliferation risk. And such reactors are typically in the realm of research reactors. There are some examples of reactors in the range of 40 to 100 megawatt thermal that would then be consistent with this ability to produce up to one significant quantity of plutonium per year. So there's a concern about monitoring not only the plutonium inventory and production in power reactors, but also in research reactors. With regards to how the plutonium production and all the other non-proliferation activities are being implemented worldwide, there is a legal framework that exists in the form of a number of treaties, such as the non-proliferation treaties. And there's also international organization, the International Atomic Energy Agency, or IAEA, which is a steward of those of various safeguards practices that promote the objectives that have been defined under these treaties. And some of them are listed here. So for example, in the realm of declared nuclear facilities and nuclear materials, there is a need to detect their diversion and misuse, and as well as the undeclared production. But there's also a desire and need to detect undeclared nuclear facilities, materials, and activities. So all these things are important. If we focus on the current reactor safeguards, there are several measures that are considered there in the context of safeguards. And One is checking input and output declarations, accounting for different items, and then containing and performing surveillance. Now, IEA has also recognized the potential of antineutrino detectors to and antineutrino-based monitoring to support these safeguards objectives, and he has examined that in several times. So this is an example of one of the reports that has resulted from these discussions. So focusing more on the problem of discovery and monitoring of undeclared reactors, which by its nature has to be done remotely, there are certain methods that exist today that have been developed, that have been used for a long period, and they include both technical and intelligence methods. So in terms of technical methods, we have a combination of satellite imagery, airborne radar, imaging in the thermal infrared region, which can penetrate, or imaging in different parts of an electromagnetic spectrum that can penetrate clouds, for example. There is detection of radioactive releases, radionuclides, as well as chemicals. And there are also other methods such as geophysical surveys, tracking of the supply chains, and of course, traditional gathering of intelligence. Especially those technical means have several limitations, and one of them is they usually operate intermittently, so they're not pervasive. They can be relatively unpredictable in the efficacy of data collection and the magnitude of the source term which is being collected. They typically have limited geographic coverage, so there's some queuing needed. There's usually a trade-off between resolution and the field of view, for example, for surveillance. So some queuing is needed externally in order to focus the attention to a particular area, and the thermal signatures can be masked. So all of these are some of the limitations that have been identified for the current methods. And that brings us to neutrinos, and I'd just like to spend a few minutes saying a few words about what they are and how they're detected. And I believe there will be another lecture in this series, which will also talk about antineutrino detection. So I will try to stay to the minimum at this and talk more about the use cases. So looking at the at the standard model of elementary particles, which no doubt I think all of you have seen. Neutrinos are located at the bottom here. They're the leptons, and they have several characteristics. They're neutral, they're stable, and they appear to be elementary particles. They come in three flavors: electron, muon, and tau. They have a small but a non-zero mass, so that's a discovery made approximately 20 years ago from oscillation experiments, and they also, all of these things are true also for antineutrinos, except that the antineutrinos also have a property which is called the weak charge, which is opposite of neutrinos. With regards to sources in nature, there are many. Such as cosmic ray showers, natural radioactive decay, and then the PP fusion process in younger stars, which is the source of the fusion energy in those stars. So those are all sources of neutrinos that are present in nature. Now, with regards to anthropogenic antineutrino sources, those have been developed, and now they're very common in the nuclear age. And essentially, all of them result from the artificially induced fission. And so this illustration here shows an example of neutron-induced fission on uranium-235, which produces two fission fragments. So the two example fission fragments that are given here, which are born with excess neutron number. And as such, they like to undergo beta minus decay. As they undergo a chain of these beta decays, they emit antineutrinos at every stage. So there is a whole process by which, then these antineutrinos emitted with some time characteristic following radioactive decay. I already mentioned nuclear reactors as sources of neutrinos, but there are also other anthropogenic sources, such as nuclear explosions, and then also spent nuclear fuel and fuel reprocessing waste. And in all of them, the main origin is the beta decay of the fission fragments. With regards to the lifetime, in nuclear reactors, we see quasi-state, steady state emission over days to months, whereas in nuclear explosions, we see intense bursts over a few seconds. And then finally, with spent nuclear fuel and fuel reprocessing waste, we would see low-level emission that exponentially decays over many years. Energies also are from nuclear reactors and explosions extend up to about 8 MeV. And with regards to spent nuclear fuel, the spectrum of antineutrinos from those sources is softer, so the energies are lower. Now, I did mention that we have gone a long way from Pauli's initial statement that antineutrinos are undetectable. So in fact, 26 years after he has proposed the existence of a neutrino, neutrino was actually detected directly in a reactor experiment with a detector which very much looks like something that one would use today for what is called near field detection. So detection of neutrinos are relatively close to reactors. This was called the Project Poltergeist. This was the famous Cowan and Rines experiment, which was done at two laboratories. One was Hanford, the other one was the Savannah River laboratory. And as a result, so we see that the whole idea of antineutrino detection as a method for monitoring nuclear reactors naturally stems, from this kind of proposition. So moving on to a question of how nuclear reactors emit antineutrinos and how strong sources are. First, we need to recognize the antineutrinos emitted isotropically. They cannot be effectively shielded, so they will be emitted in all directions, from a core of a nuclear reactor. And a typical number of antineutrinos, the rule of thumb is that 6 antineutrinos are emitted per fission, and they constitute about 4% of the energy of fission. And to the first order, one can estimate the flux of antineutrinos from a nuclear reactor to be proportional to the thermal power of the nuclear reactor, or the fission rate in a nuclear reactor. So one particular characteristic of operation of a nuclear reactor is that the composition of the fuel in the nuclear reactor changes as it goes through its fuel cycle. As a result, there will be different contributions of fission that occur at different times during the fuel cycle, depending on what fraction of these nuclides contributes to the power production. These different nuclides, as they undergo fission, they result in different fission products that undergo different fission chains, result in different spectra and quantities of antineutrinos emitted. And the result of that is that as one goes through the nuclear fuel cycle, there is a different number of antineutrinos emitted, which is illustrated on this plot below, which shows sort of the cross-section for one of the detection methods, which is called the inverse beta decay, per per fission process, per fission reaction. And one can envision sort of the area under these curves, you know, being proportional to the rate of detection. I'd like to say a few words about how neutrinos and antineutrinos interact. And the most common way to detect antineutrinos is called inverse beta decay. So in the inverse beta decay, antineutrino interacts with a proton, produces a positron and a neutron. And so positron, so the detection of the antineutrino then constitutes coincident detection of a positron and a neutron. A neutron is typically captured on a medium such as, on a nuclide such as gadolinium that is introduced with its large cross-section. So this is technologically mature. It's sensitive to flavor, so it works with antineutrinos but not neutrinos. It does have a threshold, so it will not see any antineutrinos below 1.8 MeV. Cross-section, importantly, is fairly large. You know, so if you look at here, the comparison of different cross-sections, you know, for antineutrino interactions, this is the one that is very, very promising in terms of practical applications. The other one is electron elastic scattering, where electron scatters off of, an antineutrino scatters off of an electron, and this is reaction which has no threshold. It's highly directional, but it does have relatively low cross-section, and it's fairly, so the cross-section is here, and it's susceptible to different backgrounds. And then there's a really interesting way how neutrinos interact by coherently scattering off of the entire nucleus, and this is called the coherent elastic neutrino nuclear scattering, or CEMENT. And this has been experimentally demonstrated only 2 years ago. This reaction has no energy threshold. It has the largest of all cross sections, but it's flavor blind, so you can see also neutrinos, and it's extremely difficult to detect, as you can imagine, if it was only 2 years ago that it was seen for the first time. So let us just look at how difficult would it be to detect the reactor using a method which has a large cross-section, such as inverse beta decay, which is relatively mature. And one of the things we've already seen on the previous plot is these cross-sections are fairly small. So if you look at the scale here, inverse beta decay is this red line, and then this dashed blue line is the electron scattering. And so you see these numbers are very small, so we are accustomed, at least in nuclear engineering, something on the scale of a barn, which is 10 to the minus 24 square centimeters, and you can see that this is many, many, many orders of magnitude below. So, and the reason it works is simply because the number of antineutrinos that is produced is fairly large. So taking 6 antineutrinos per fission and about 10 to the 21 fissions per second in a 3 gigawatt thermal reactor, you get something like 10 to the 22 antineutrinos per second, unattenuated and emitted in all directions. So if you place your detector at some distance, such as 25 kilometers, you will see why I'm using 25 kilometers now here. You find that if you take a 1 kiloton of water, you will see something like 3 inverse beta decay interactions per day. So it is not a very large number, but then let's consider that the fact that the water is a relatively inexpensive medium, and it's important to actually look at you know, how these statistics of these interactions, the statistics of events in these detectors lends itself to some conclusions about the operation of the reactor. So, so based on this, several use cases have been developed for the use of large detectors for reactors far away, and one of them is the discovery of undeclared nuclear reactors, where a signal is detected at long standoff. We don't know where the reactor is, but the detector can look at region that is on the order of maybe 10 to 100 kilometers and look for such for signals that are consistent with presence of reactors that are not declared. And the other use case that has been proposed was the monitoring of operation of the known nuclear reactors. So we have frequently a situation where nuclear power plants have multiple cores, and maybe we have situations where a single core is operating, the other one is turned off. And we'd like to see examples of, for example, such shutdowns or undeclared operations, which would then be potential for plutonium diversion. And in this case, signal cannot be shielded. So this is really what is very attractive about the whole scheme. So in order to explore these various ideas related to antineutrino detection, a collaboration was formed several years ago, which is called Watchman Collaboration. Watchman stands for Water Cherenkov Monitor for Antineutrinos. It has grown since. It's a group of US universities, UK universities, and several national laboratories in the US as well as the UK. This is a picture of our collaboration in happier days when we could meet in person. I think this was taken 1.5 years ago in Scotland. And this is also a picture of a group from our collaboration underground at the site where the demonstration experiment is planned. So the sponsors in the United States and the UK have also developed an infrastructure, a formal infrastructure that will allow this collaborative proliferation research, non-proliferation research related to antineutrino detection to be exercised. And this is called the Advanced Instrumentation Testbed, or AIT. And the goal for the AIT is to permit real-world at-scale testing of monitoring capabilities for nuclear reactors. And that includes various things such as testing different detector designs, detection media for the detectors and algorithms. And the whole setting, for the AIT looks something like this. So there's a power reactor called the Hartlepool reactor in northeast England, which consists of 2 cores. Each one is about 1.5 gigawatts. And a 25-kilometer standoff, from this source, from these reactors, is an underground laboratory. It's a scientific laboratory, which is also a commercial mine. And this is called the Bowlby Underground Laboratory. And the AIT will then support the deployment of several experiments at this underground laboratory. And the first one will be called Neutrino Experiment 1, and we like to call it NEO now. This will be followed by future experiments that you call NE2, etc. So now I just want to say a few words about how the detector may like. And as you may suspect, it's a large detector. So this is sort of very preliminary, and many different designs have been already simulated and tested, but it's safe to say that this will be a large underground tank with a detection medium which allows scaling to large volumes, large masses. So it will be based on cheap materials such as water or water-based, another water-based material. It will be doped to enhance the neutron capture with gadolinium. The mass will be on the order of several kilotons. The light that is emitted, from this detector will be measured by thousands of photodetectors. And it will be located in this advanced instrumentation testbed, which is a mine about 1 kilometer deep. Initially, we will be based on the inverse beta decay, but there's also talk about looking for electron scattering as well, which I talked about. And it will support various upgrades in the future to test things like new detection media, photosensor tests, and enhancements of the purity that will allow some new detection modalities to be explored. So just a few words about how antineutrinos are detected in water that is doped with gadolinium, which is one of the primary contenders, for detection media in the first neutrino experiment in the advanced instrumentation testbed. So what you see to the left is antineutrino interacting with the proton. You have an emission of a positron, which emits what we call a prompt signal, which is a Cherenkov emission of light, which is detected as a prompt signal. And inverse beta decay also produces a neutron, which thermalizes. It travels in water, and it gets captured on gadolinium. And gadolinium emits something like 8 MeV of energy through a gamma cascade, which is also recorded then as a second powerful flash of light. So we're looking at coincident flashes of this prompt and delayed signal, which are usually separated by on the order of 10 to 20, 30 microseconds, depending on gadolinium doping. In this kind of detectors, event reconstruction performance, so finding out the position and energy of all of these events is very important for rejecting different backgrounds. And backgrounds are, backgrounds are everything here, because remote detection requires a large detector, but then that also increases the need to understand the background. And background has been studied extensively, not only for this purpose, but in other large detectors. And what's been found, in the context of antineutrino detection is that there are two irreducible backgrounds which originate from interactions of muons with the environment in the detector and also outside the detector. So the first one is the passage of muons, energetic cosmic muons in the nearby materials such as rock in a mine, which produces energetic neutrons. And as these neutrons can be produced in coincidence, several fast neutrons can be produced and interact in detector and produce two correlated events which look like a neutrino. The other one is the passage of a muon through a detector, which produces certain radionuclides, dangerous radionuclides, which produce a signal which mimics that of the inverse beta decay. So one way to reduce these backgrounds is to move underground, and backgrounds have been studied in preparation for these future experiments at the Kimballton Underground Research Facility in Virginia. So a couple of the measurements have been made to try to assess the magnitude of these backgrounds at different depths. And the first one is this fast neutron background. And as I said, as one moves underground, one can reduce the muon intensity. So you can see how muon intensity depends on the depth. Depth is usually measured in the units of distance times water equivalent. So this, for example, here is the kilometer water equivalent, or the shielding, which is equivalent to that thickness of water. And so you can see how, how this differential muon intensity drops. And as a result, also the neutron flux drops. And as you can see, something like a little bit less than 1 order of magnitude per kilometer water equivalent. The Watchman collaboration has actually used a detector that is called the MARS, so multiplicity and recoil spectrometer, to measure these backgrounds already. The other one is the radionuclide background, which is induced by muon-induced spallation in water, which produces nuclides that are kind of exotic. I think we don't really usually talk about these nuclides, such as helium-8 and lithium-9. They decay with fairly high Q value, but most importantly, they don't decay very quickly. So even though these muons can be identified as they pass through the detector and one can beat out such events, the subsequent decay of these radionuclides which are produced can indeed mimic antineutrino signal. And it does that because these are typically beta neutron decay. So there's a beta decay followed by neutron. So something very similar to what you will see with inverse beta decay. And a smaller detector, which is called the Watch Boy, this is like a little watchman, was built and tested at 400-meter water equivalent in the Kimballton mine, which this was a 2-ton detector, which basically confirmed the rate of these production of these radionuclides, which then informs the design of a larger detector. And then finally, there's also a background as we move further away from the reactors. We also have background from the world reactors. And this is an example of how that world reactor and neutrino signal looks like in apparently in the post-Fukushima world, where the reactors in Japan are turned off. So you can certainly see where the nuclear power is distributed. And this reactor antineutrino signal ultimately at long distances is something that constitutes a valid background for a detector that seeks to discover a nuclear reactor. And there are really interesting tools that you can play with at home. One of them is called geoneutrinos.org, which is a tool that allows you to estimate the rate of neutrinos at particular location. So in this particular case, I chose to look at the anterneutrino flux and contributions from various reactors nearby, near my house. And so what I see here is, basically contribution from different reactor cores, all the reactors in the world. And this gray gray contribution is just from the closest core. And there are other contributions here from geoneutrinos, for example. Notice that these end at about 3, they sort of, they have softer spectrum. So that detection of these anterneutrinos at larger energies is really exhibits fairly low background. And you can see some of the locations of the nearby reactors here labeled as green. So as I said, detectors need to be placed deeply below ground. At the underground research laboratory in Bolby, they will be placed at about 1 kilometer, just a little bit more than 1 kilometer, which constitutes about, something closer to 3 kilometers of water equivalent shielding. One thing about this particular facility, it's also relatively low in radon concentration, which is one of the backgrounds for these detectors, which will allow certain measurements and potential upgrades that may allow detection through methods other than the inverse beta decay. So about 2 years ago, a group got together which examined sort of various opportunities to detect anterneutrinos of a range of different scales. And we have identified a couple of scales, which we call the following. We call them on-site, which is 20 to 200 meters. Then outside the fence, which is 0.2 to 2 kilometers. Something we like to call a theater, which is 2 to 20 kilometers. And then something we call regional, which is 200 to 1,000 kilometers. And then we have looked at various use cases for these. And I think what is most pertinent to discussion today is what one can do at these longer distances. So for example, 2 to 20 kilometers, we can monitor operating status of a single or multiple reactors to exclude the existence of undeclared reactors. At even greater distances, it's possible to confirm the presence or absence of any reactors above some thermal power or the total thermal power within certain observation radius. And then as we try to go beyond 200 kilometers, it becomes exceedingly difficult, which because of the backgrounds from the world reactors, and it appears that the probable use cases then would require that we have directionality, so we can detect an anterneutrino direction, not only flux, so we can reduce backgrounds. At greater than 1,000 kilometers, even if we choose a 1 megaton detector, which is, which if you think about it, it's 100 by 100 by 100 meters of water, and it's kind of a practical limit in the opinion of this group for detectors. Then we would be facing insufficient signals. So this is something that it seems like a non-starter, something we call the very far detection. Now, Watchman collaboration is kind of interested in this region, which we call something like theater or regional detection. With regards to various sizes and deployment considerations versus benefits, so if you look at different distances, the types of detectors that you need, for monitoring nuclear reactors grow quickly as distance increases until you reach something about a megaton. So we don't really consider anything beyond that. And deployment depths that are possible these days are surface, so these very close detectors, they've been demonstrated now to be possible to operate them near the surface. But as we move further, we have to move underground, and then for this further detection, we have to go deeper underground in order to minimize the background. There are a couple of benefits here of this operation. One is persistence, ability to detect or exclude reactor activity in a wide geographic region without external queuing information. They're not sensitive to weather, shielding, or other environmental factors. And they can place constraints or directly measure the operational status and thermal power of a reactor. So one can estimate the maximum possible rate of plutonium production in a discovered reactor as well. So all of these are potential benefits. With regards to remote monitoring of the Hartlepool reactor at 25 kilometers, there's some analysis of the use cases that is in process, and there are also some preliminary results that have been presented already. Now, those are really subject to change because there's many assumptions with regards to detector operation and detector implementation that go into them. But here's one example. Let us assume that we want to know that the Hartlepool complex core in operation schedule is known, and we want to know how many days it takes until a 6 kiloton water detector doped with gadolinium confirms observing the reactor on-off cycle with a confidence level of 95%. And this is the result of one of such initial calculations, which is similarly being revised, but kind of you get the idea of how these calculations are conducted. So as you can see, this is, on the vertical axis, you have the confidence limit. On the horizontal axis, you have the experiment day. And this particular analysis then corresponds to that confirmation of observing the on-off cycle, where, also there are certain declared maintenances and shutdowns, that are also indicated here with this, with these lines of different colors. And you can see we can expect confirmation in something on the order of between 100 and 200 days. And then as we go to higher confidence levels, it's obviously takes longer. But like I say, this is really preliminary, subject to analysis, and there's a lot to be developed. But I think this is kind of the idea of the studies that need to be done for these large detectors. So for the far field, I just want to reiterate what kind of measurements are possible, and the obvious issue there is that event rate drops, so one cannot measure the fissile content in a timely manner. But what's possible is to discover or exclude the existence of undeclared reactors in the region, constrain their power output over a period of months. So one can place an upper bound on fissile material production. One can discover undeclared reactor by looking for signal above the known background, and maybe observe basically a very large change in reactor power, which is manifested as deviation from a stable background, which is not known but is stable. With regards to problems, I already mentioned the cross sections are still small. There's not much that can be done about that. Backgrounds are quite uncertain, and there's also the background from other reactors. And there will be also persistence of the cosmic background, which kind of dictates this underground deployment, which obviously is expensive. So looking further, if one wanted to detect a 50 megawatt thermal reactor, and which we use as a standard candle, for production of plutonium, then let's look at just a very, very ambitious goal here, which is excluding the presence of such a reactor within 1 year with 95% confidence level at 1,000 kilometer standoff. And the result of this calculation tells that one needs a 335 kiloton fiducial mass of a water-based detector. So it is a very large detector, but the assumptions are also just very generous, I would say. One of them is 100% efficiency above a threshold of 3.26 MeV for interaction that happens, that there are no observed events, and that the background is Poisson distributed and it's consistent with zero. So these are very generous assumptions, and there's some more realistic ones that are tabulated in this plot, also described in more detail in this paper, that look at sort of that tabulate the use cases in terms of the mass and kilotons multiplied by the dwell time in years required to detect reactors at different distances. in the cases of low, medium, and high background from the world reactors. So next, I just want to highlight that there are some new technologies on the horizon which can improve upon these current estimates. And the first one is the advent of a medium which is called the water-based liquid simulator. So I talked a lot about the water. Liquid simulator is a very common detector for antineutrinos for smaller detectors. For larger detectors, it would become very expensive. But the idea behind this technology, which was developed at Brookhaven National Laboratory, is to basically surround the simulator, such as a linear alkyl benzene like LAB, with surfactant, such as this compound here, which then allows sort of the micelles of simulator to be surrounded, by surfactant and immersed in the water. And in fact, such liquid simulators can then be additionally doped with maybe even doped with the neutron capture agent. And it can be mixed into water with different fractions. And it's it would be significantly less ultimately expensive. It has the potential to become much cheaper than liquid simulator itself. Now, it has one special capability is that it produces both Cherenkov and scintillation light, and that Cherenkov and scintillation light can be detected simultaneously, which offers some new capabilities, such as better identification of particle, higher light yield, detection of particles, directional detection of the particles, efficiency of neutron tagging, low threshold, good energy resolution. So that's one technology, but the other one, which is also necessary to use such a water-based simulator, will be also a large detector, which is very fast. And so there is a technology called LAPPD, which is the large area picosecond photodetector, which has all the nice, it's microchannel plate based. It's been developed at the University of Chicago, now commercialized. It has a very fast response. It allows very good reconstruction of the events in these large detectors. So they can, that is also one of the things that is looked at. And then finally, the other thing is, the final thing is the antineutrino directionality. And as I mentioned, electron scattering is a method to get directionality. So this has been studied through a set of simulations, which show essentially that there is the potential, for use of this interaction mode, not only to detect neutrinos, but also to point to the direction of their production. Now, of course, there are issues, and one of them is that the cross-section is significantly smaller than the inverse beta decay, but in a detector, such interaction may be detected simultaneously with the inverse beta decay. And the main challenge here is that a very high level of purity is required, for this type of detector. And this is a typical radon contribution to the signal that would occur in such a detector. So you can see the dominant contribution to the signal would be radon, whereas the electron scattering signal would be buried well below. And in order to suppress this signal, one would need to reach purity levels which are about 100 times better than in some of the physics experiments that have been deployed currently. So there are ideas how to do that. It's not necessarily impossible, but it is a difficult problem. And one thing that I also wanted to say, which I don't have a lot of time, but I'll say that there's a problem also of using antineutrinos for comprehensive testband treaty, which has been studied for a couple of times. And so this is the idea of detecting nuclear explosions or confirming them with antineutrino detectors. And one of the recent contributions to that field has been this idea that one can use a seismic queuing. So one can use the seismic signal, the earthquake-like signal, as a trigger for the analysis of such detectors. But still, the conclusions, from these studies really show that it would be very, very expensive and doesn't appear practical immediately to do this. So there has been a lot of community interest in this area, and I'll just say that about 2 years ago, a group gathered, which last year developed the strategic survey of anti-neutrino-based proliferation technologies, which I invite you to review, which is available from as a Lawrence Livermore National Laboratory report that talks about various applications. And there's also a companion article, which was recently published in Reviews of Modern Physics, which outlines in more detail some of these cases for applications, which I just talked about. There's also a community study, which has been commissioned recently to look at various applications for neutrinos and in nuclear energy as well as security. And I just don't want to dwell on this too much. I'll just say that there are many different things that have been considered. I talked about this regional reactor discovery, exclusion, and monitoring, but if you go to the website, which is open, you can look at some fact sheets there, which talk about all of these other possibilities for the use of antineutrinos. To summarize, I talked about the regional discovery and exclusion of small reactors, which is still an unsolved problem for nuclear non-proliferation, and monitoring of large power reactors could also benefit from improved safeguards. We saw that antineutrinos interact weakly, but they're also detectable from intense enough sources, even at these long distances. And because we operate at these long distances, it's really important to understand the backgrounds. And there are many different backgrounds: environmental, instrumental, and the ambient from the low power reactors. And finally, looking at the immediate future, it looks like the underground large volume detectors that are based on water or water-based insulator will offer relevant sensitivities for non-proliferation applications. So with that, I thank you for your attention, and I'll take any questions. And I think I can see the chat here. So I will just go through the questions in the Zoom group chat. And I see the first question from Asselbeck. And the question is, I have seen in one of the Russians' nuclear power plants how they capture antineutrinos in pools. If I'm not mistaken, they use kind of old style TV screens. Would you mind to explain how antineutrinos are captured? And I suspect that this is probably one of the near field detector tests where antineutrinos are being not quite captured, but they're being detected. And because of the proximity of detectors to the nuclear reactor, they can be detected with appreciable rates, just in the manner that I described earlier. So the next question is, what causes the sharp dips in the neutrino spectrum near my house, and not just near my house, but also elsewhere? And so there are a couple of reasons, for these dips, and one of them is certainly the spectrum from the beta decay of various nuclides, but also there is the property of neutrinos, which is called oscillation, where neutrinos are detected with different probabilities as a function of distance, and all of these things kind of contribute to these variations. So as you can imagine, there are sources of neutrinos at considerable distance, from my location, so they can be seen as producing these variations. Next question is, what is the impact, if any, of the coherent experiment, observation of coherent elastic neutrino nuclear scattering? And I would say that it's a very important experiment. Coherent experiment has observed about 2 years ago the first coherent neutrino nuclear scattering for neutrinos that are produced using an accelerator. So this was a very important confirmation for one of the predictions of the standard model. So this is a very difficult detection, but it does offer some special opportunities for non-proliferation as well in the future. So as of now, we haven't detected any neutrinos from nuclear reactors using coherent scattering. So that has not been done yet. It is considerably more difficult than experiment with accelerator. But such reaction, which has no threshold, would allow observation of much softer neutrino spectrum, for example, from spent nuclear fuel. And as well as it would also enable perhaps smaller detectors for monitoring nuclear reactors, simply because the cross-section is higher. And the next question is, are antineutrino-based detectors used for space-based nuclear 3D verification? And I think the answer here is not, I would say no. If a large antineutrino detector is developed, it would automatically become capable of detection of any kind of source of antineutrinos as long as the distance from that detector is not excessive, based on these considerations that I talked about earlier, based on the limits on the size of detector and the size of the signal that may be produced. And the next question here is, you talked about using gadolinium water as a medium. I've heard about ice medium lab in Antarctica. Are there any other media that can be used for neutrino detection? And yes, absolutely. So this is a very famous neutrino experiment, which is called the ice cube in the Antarctica, which detects very high energy neutrinos that originate in space. So such detector is not suited, for non-proliferation use for detection of antineutrinos, much lower energy antineutrinos, from reactors. And it's also not gadolinium doped, obviously. It's just, it uses simulation in ice or Cherenkov emission in ice. But there are certainly other media that can be used. So any medium, for example, that will support, that has a large number of protons, a large amount of hydrogen, will be suitable for detection. So for example, liquid simulator is very commonly used, and not just liquid, but also solid state simulator has been used recently as a method for neutrino detection. And then something we talked about earlier about the coherent scatter or the sevens detection, which can in principle use any nucleus as long as the recoil of that nucleus can be conveniently measured. So all of these possibilities exist because neutrinos interact, and the question is, which media are just convenient to extract the signal. Are there any other questions?
All right, thank you very much, Professor Jovanovic. If you want to wait around just a couple more minutes to see if there are any additional questions, otherwise I think we're good for today's lecture. Thank you all for joining.
Thank you very much, and I very much enjoyed it, and I welcome questions. I think you've seen my my website address, and it's not hard to find me. Just Google me. I'll be happy to chat more. Thank you again.